Okay, I guess that means we can start. So welcome back to this set of lectures. Today we come to the main subject of the course, namely the soft-collinear effective theory. Sorry, I will. In short, SCET. And let me just briefly repeat what I said already yesterday, namely in QCD or generally in quantum field theory, it was really a long-standing problem how to basically account systematically for long-distance effects in cases where there is no Euclidean operator product expansion. The operator product expansion is a rigorous tool allowing you to perform a power expansion of Green's functions, but it really rests on Euclidean processes. So basically, if we have processes with energetic light particles, where light really means basically massless, and energetic light particles pose problems. And for instance, in the last decade of the last millennium, there was a lot of efforts on using tricks to learn about power correction to LHC processes. So for instance, people studied what's called renormalons, certain terms in the higher order perturbative series that can give rise to power suppressed effects as a model for a more systematic treatment. But really, the systematic framework is offered by this soft-collinear effective theory, and in that sense, it's also really a big breakthrough. What's the problem with energetic light particles? Well, you have P mu, the momentum vector of these particles, which is, their energy, and then their free momentum. And the point is, for an energetic particle, the energy can be very, very large. However, P square is small. So P square is typically the mass of the particle, okay? So if it's on shell, P square is m square, and it can be much, much less than the energy square. And we will consider an example, and the example is the simplest one you can think of, E plus E minus to two jets. So, at the parton level, you collide electron-positron and you produce a quark-antiquark pair, and then these quarks hadronize, they radiate gluons, and then they create jets. So, roughly speaking, we have a virtual photon here, some gamma star with some momentum transfer q square or some energy square root of s, which come from the plus E minus that collide, and then we create basically two jets of particles where the particles may contain the original quark-antiquark that was produced here, and then additional radiated particles, right, that come off these original particles. So we build up these jets basically of particles outgoing. And of course, we can assign a momentum to the first jet, a total momentum to the first jet, jet 1, and we can assign a total momentum to the second jet, number 2, going in this direction or this direction, and we can also align the jet axis with the z axis. Okay, and then if we do that, so if I point this into the z direction, then these four momenta of jet 1 and jet 2 can be written in the following form. I just write them in their components. So, of course, this is for the total jet, not for a particle inside the jet. That's the total jet momentum. So the jet has some energy, E1 and E2. And now I align the z-axis such that in the xy entries we find zeros here. And then in the C entry we have E1 squared minus mj1 squared, the square root of that. So positive value along the z-axis for z1 and negative value for z2, where this is E2 squared minus mj2 squared. Okay, and mj1 square, mj2 square are the invariant masses of the jets. So p ji squared, 4 momentum squared, is what I define to be the invariant mass of each jet. Okay, now moreover, we know that, well, of course, we have momentum conservation, so this quantity is equal to this quantity up to a sign, so the total momentum is 0, and the two energies add up to give the total energy, which is square root of S, the center of mass energy. And if it wasn't for so if I work in the limit that the masses are much less than the energies, then you can neglect this m square here to first approximation, and then you see that E1, apart from small corrections, is equal to E2, is equal to 1/2 the center of mass energy. And that is the large scale. So this is the hard scale of our problem. The total center of mass energy, that's the largest scale in the problem. And then the small scale is the jet masses. So mji squared, much, much less than S. These are the small scales. So, you know, it resembles a bit the case of HQET, where we had a heavy quark mass and lambda QCD as two very disparate scales. Here we have the jet masses and S as the high scale and the low scale of the problem. But you also see it's intrinsically Minkowskian. I mean, in this 4-vector, each, you know, the components individually are very large, but when you square the vector, they almost sum up to 0. So the question is really what's there to integrate out in such a process? How would you use effective field theory technology to simplify this process? And for a long time, this was basically completely unclear. Now, what we certainly can do, we can identify an expansion parameter, our little lambda. I think I should write larger again. And the little lambda, let me define the little lambda to be the jet mass divided by square root of S. And let me also call Q square root of S, so I don't need to write square roots all the time. So Q is the hard scale, jet mass is the small scale, and by assumption, this is much, much less than 1. So that's our expansion parameter. And on top of that, we're now going to go to a more suitable coordinate system. This here I'm using Cartesian coordinates where I have the time axis and then x, y, z. But if we have particles moving, very light particles moving in certain directions, like the z-axis in this case, it's advantageous to introduce a different choice of coordinates. And to this end, we introduce two light-like reference vectors. These reference vectors, so they are analogous to my velocity vector in heavy quark effective theory, except this was not light-like, this was time-like. The light-like reference vectors, they're always called N. N stands for null, because if you square these vectors, they give 0. So I define n mu to be basically a vector that has a 1 in the time component and now a 1 in the z direction. And you see this is reasonable because if I'm neglecting m compared to the energy, which is a good approximation, this first jet is E1, 0, 0, E1, so it's E1 times this vector, basically. And notice that this n squared is not 1 like in HQT, it's 0. And then we introduce a second vector. I'm going to call it n bar as a null vector in the opposite direction, so in the negative z direction. And also this squares to 0. Some people call this n plus and n minus. Some people call it n1 and n2. Up to you. As long as it contains an n, it's okay. Notice there is a normalization condition here that n times n bar is not 0. It's also not 1. It's 1 times 1 plus 1 times 1, so it's 2. You could rescale them by root 2, and then they would multiply to 1. Also in some papers you see that people do this. Now what's important is we can now, instead of writing vectors in x, y, z components and time, we can write vectors now in a new coordinate system where we still keep x and y, but instead of time and z direction, we keep n and n bar. So if you wish, this is the light cone directions, right? In the light cone diagram where you would have time here and let's say c here, the light cone would be defined by these lines, and this is exactly the directions in which these vectors point. So we can now, for an arbitrary vector n, p, but p is not any, well, actually, let me do a new symbol here. Yeah, doesn't matter. So generic vector p, not necessarily these vectors. Any 4-vector p can be written in the following form. It's not so hard to remember. It has a piece in the direction of n bar, and it has a piece in the direction of n, and then it has a piece in the direction of x and y. So the component along n bar happens to be n times p. The component along n happens to be n bar times p. And the components in the x and y direction I will simply call p perp. And I mentioned yesterday that I will introduce a new perp meaning today. From now on, until the rest of the lectures, perp from now on refers only to x and y. So in SCED, we always have the z-axis will always be the direction of large energy flow, and x and y is simply orthogonal to that direction. So this is the xy components of the vector. And you know that this is correct, you can see by simply, if you multiply this with n, you get n dot p. Here you get n times n bar over 2, which is 1. Here you get n squared, which is 0. Here you get n times p perp, which is also 0. So n times p perp is 0, and n bar times p perp is 0, because n and n bar contain 0 and 3 components, and the perp direction is only in the 1, 2 components. If you multiply with n bar, this gives 0, this gives n bar dot p, this gives 0, and the perp components are simply perp components. So whenever we have a 4-vector, we'll write it in these, this is called the light cone basis representation of 4 vectors. Notice also, if we take a product of 2 vectors, p1 times p2, with this formula, you find that this is 1/2 n times p1 n bar times P2 plus 1/2 n bar times P1 n times P2 plus P perp 1 times P perp 2. And when you square a vector, this reduces to n dot P n bar dot P plus P perp squared. So these are simple rules, but we'll use them over and over again. So better get used to it. Okay, so what we're going to do now, we're going to take our jet momenta and look at the light cone components of these jet momenta. So for our jets, we have the following components. Let's do jet number 1. So we start with n dot P. N dot P, we have to take the dot product of this light cone vector with this 4 vector. Remember that the Minkowski metric has a minus sign in the spatial components, so we get 1 times E1 minus 1 times the square root. So we get E1 minus square root of E1 squared minus mj1 squared. And remember that we are assuming that E is much bigger than m. If I neglect m, these two terms cancel. If I do the Taylor expansion, then the first term I find here is mj1 squared over 2e1. Of course, this is the first term. Then there would be higher order corrections. And 2e1 is approximately equal to square root of s, which I call q. So this is the same as mj1 squared over q, again up to tiny power corrections. And this is the same as q times lambda squared. So if I measure the size of this component in terms of the hard scale, I find it's much smaller than the hard scale by 2 powers of lambda. So that's the small component of this jet momentum. If it has a small component, it is also likely to have a large component. So, sorry, this was J1. So n bar times J1, the only thing that changes is the plus sign. So the minus sign here becomes a plus sign. And now the leading term is simply, I can drop this m, then I get 2e1, which is the same as q. So you see the n bar dot p component is large. It's of order the hard scale. And the perp component, by choice of reference frame, the perp component of this momentum is 0. I could have chosen the jet axis a little bit away, then it would not be exactly 0, but with this choice it's 0. So this was jet 1. And for jet 2, well, it's obvious what happens. The only difference really is this sign. So for jet 2, the role will be interchanged, right? So n times pj2 will be lambda square q, will be q, sorry. N dot p will be the large component. N bar dot pj2 will be lambda square times q. And again, the perp component by choice of the jet axis is 0. Okay, so we see it's useful to define these vectors n and n bar simply because if I project we will call such a jet, a bunch of collinear particles, collinear with a certain direction, the jet axis. So if we consider a jet of collinear particles, then in the basis where we have this light cone decomposition, one of the components is very small, one of the components is big. Whereas, in this way, every component is big, but it doesn't express the fact that two are equal and opposite sign and maybe cancel in the sum order. So this is a more useful way. Now, that's for the jets as a whole. What if we look at particles inside these jets? Okay, so these jets are built up of particles. All the particles move along the z direction with very high energy. So basically the particles inside the jet, they will have similar scaling. The sum of their momenta needs to build up the total jet momentum. So for the particles inside the jets, basically we can assume the same components for the same scalings for jet 1. Here, basically a particle inside jet 1 will have the following properties, that n dot p of such a particle and n bar dot p of such a particle and p perp of such a particle will scale as lambda square 1 and question mark times q. In the sense that, for on-shell particles, these products, n dot p and n bar dot p, for each particle, it's the energy plus or minus the size of the momentum. That is always positive. This can never be negative for an on-shell particle. So all of these things are positive, and if we add them up, they have to add up to the total jet momentum. And generically, the particles inside the jet all carry large energy in the jet direction. You could be unlucky that in one case, one of these particles has zero momentum, for example, then it doesn't matter, doesn't have any effect on the sum, but generically, this is the scaling. These n dot p components all need to be small because their sum is small. The n bar dot p components can be big because their sum is big. And what about the perp components? The perp components of the total jet is zero. The perp components of the individual particles doesn't need to be zero. You can also see this from the drawings. Some particles go a little bit in the upper half, some particles go a little bit in the lower half. On average, the p perp is zero. It turns out the right scaling here that you can allow is up to order lambda. And the reason is that each particle in the jet will also satisfy a mass condition, but this is now the particle masses, the quark masses or the gluon masses, let's say. And if p square is going to be small, p square from this formula is the product of the two light cone projections. One is lambda square, one is lam. So for instance, this would be lambda square and this would be 1. And then the p perp should satisfy the same scaling. So the p perp squared should also be order lambda square so that all terms in this sum are equally small. And that means the individual p perp mu can be of order lambda. And if we have a momentum with that scaling, so we will order the components in this way always, and if we have a momentum satisfying that scaling, then we call this a collinear particle or collinear momentum. Collinear momentum or collinear particle, I'll use the words synonymously. Okay. Sometimes people also call this an n-collinear particle. I say a word to this in a moment. This is for jet 1, for jet 2. In jet 2, it's the opposite. In jet 2, the momentum needs to be such that n dot p is the big thing, n bar dot p is the small thing. So the scaling here is opposite. The first component is 1, the second is lambda squared, the third is lambda. And that would be called different names. This would be called an anti-collinear particle or anti-collinear momentum. But instead of anti-collinear, you can also say n-bar collinear. For the purposes of this lecture, we will use collinear and anti-collinear. That's always nice if you have a 2-jet configuration. If you have 5 jets in the final state, obviously they are not all pointing in the z-axis. So then you have to define N1, N2, N3 for the directions of the various jets. And then it's better to call the particles inside these jets N1 collinear, N2 collinear, N3 collinear, as many directions as you like. But if it's 2, it's conventional to call them N and N bar. Yeah. Are you talking about rescaling these vectors? Yes. No, so you should, if you rescale them, let's say by 1 over root 2, that would be fine. You shouldn't rescale them by 1,000 or so, in the sense that, you know, you want to maintain, once you agree on a normalization, you can rescale this by a factor lambda, let's say a factor xi, and this by 1 over xi, and if xi is order 1, that's perfectly okay. Well, depending what you do, if you deform it by a little bit, it wouldn't change the scalings. If you deform it by a lot, it would not be a suitable choice. So I mean, I have a jet axis and I want to define, it's like with the velocity vector, no? I want to define the n more or less aligned with the jet axis, but you are right. If I change this definition infinitesimally, it shouldn't change the physics. And once again, this is exactly what is called reparametrization invariance in this context. So reparametrization invariance are certain relations, but we haven't written down any scat operators, so it's too early to do that. But this is relations between operators resulting from the fact that it shouldn't matter how exactly one defines these reference vectors.
So typically, if you have n particles in less than less 1, then n bar dot pi, if each particle, the n bar dot pi scales as q, then it's n q.
Yeah, you're right. So I'm not, what you're saying is that if the jet has lambda square, this may have a 7th of lambda square or something. I don't care about this, yes. You're right. These values will be smaller than for the total jet, but they will still satisfy the scaling that this component is much less than this component. That's all that I care about. So if you wish, you can divide by the number of particles here. In the sense, I could take this entire jet and boost to a frame where this jet is at rest. And then in the jet, I will have particles flying in all directions with small momenta because their masses are small. And then it's completely isotropic. And now I take this configuration and I boost it to the infinite momentum frame. And then all the particles will satisfy that their n bar component is much bigger than their n component. That's really all that matters here. Yes, and no, it cannot scale as lambda square. So it in general is much less than lambda square. It's typically 0. But on the other hand, quarks are also not strictly on shell because of confinement. So, you know, the p square of quarks and gluons is never exactly 0. It's something small. It's typically something of order lambda QCD squared. So it's, you know, let me put here less or equal to lambda squared. But it shouldn't be big. You should read this that it shouldn't be bigger than whatever I show here. Okay, don't worry. this is just the beginning, so we'll discuss this in much more detail. So here now, basically what I have assigned, I have basically decided that in this process, I'm going to call all the particles in this jet collinear, all the particles in that jet anticollinear, which means these particles are boosted. They carry large energy in a certain direction. That's what makes them jets. Now, if I study loop corrections to this process, so for instance, imagine I exchange a gluon here. If I exchange a gluon here in a loop, this is not an on-shell particle, this is a virtual particle. I integrate over all loop moment. And these loop momenta generically can also be as large as the largest scale in the problem. So basically, in virtual corrections, we can also have so-called hard particles. And for the hard particles, I will simply call a particle hard if its momentum basically has all components of order the hard scale. And I call this a hard momentum or a hard particle. And the three entries here will always be in this order. So now you could say, great, okay, so this is a bit like HQET. In HQET, we had hard modes and soft modes. We integrate out at the hard modes, and we were left with an effective theory of soft quarks interacting with soft gluons. We could try to do the same here. We have a theory of hard modes and collinear modes and anticollinear modes. We could integrate out the hard gluons and get an effective theory of collinear and anticollinear particles. And we could try to use that theory to describe this jet process. However, this does not work. This is not the whole story. So let me just put here a big but. A theory only containing hard collinear and anticollinear modes is not the whole story. And I could now tell you what you need to add to the theory to make it a whole story, but it's much more instructive to study an explicit example. And the explicit example is paradigmatic for SCET. It's the Sudakov form factor. And in fact, what I'm going to study is the off-shell Sudakov form factor. And it's called Sudakov form factor, but it's actually something very relevant to, let's say, electroweak processes at the LHC. I guess Sudakov was a famous Russian physicist, probably in the 1950s or 60s, studied this problem for the first time. What is the Sudakov form factor? You will see the relevance to this problem immediately. I'm considering a three-point function where I have a photon, can be virtual or real photon, basically a vector current as an external source with some large momentum q. And then I have a quark and an antiquark. So this is a quark, this is an antiquark with momenta p1 and p2. And I want to work in the limit where q square, which I define to be the absolute value of little q square, is much, much bigger than p1 or p2 squared. So I'm setting the masses of the quarks to 0, mi equal to 0, but pi squared non-zero. In fact, I will take it negative. What's the relevance to my case? Well, this is exactly my case. I have a photon here, which decays into quark-antiquark. Okay? Now here, the quark-antiquark then emit more radiation and I'm building up jets. I want to make a simpler case. I just study quark-antiquark. This is not physical, of course, because quarks are not physical states, okay? But this has all the features of the problem. And in particular, we want to arrange like there, we want to arrange that we have two scales, the jet scale and the hard scale. The hard scale we have here, it's the q square of the photon. The jet scale we have to put in by hand, and there's basically two ways of doing it. Either you give a mass to the quarks and you take them on shell. That's called the on-shell Sudakov form factor. Or you forget about the quark mass because it's anyway a small effect and you keep them off shell. That's called the off-shell Sudakov form factor. And that's what I'm going to study because it's simpler. On-shell Sudakov form factor is also interesting in SDT, but the off-shell one is closer to this problem. So I'm using these p-squares just as an infrared scale, just to have a small scale in the problem, because I want a two-scale problem. If I just give q square as a scale, I will get a trivial answer containing logs of q square over mu square, that's it. But I want two scales that are very different. And you can say, well, is that well-defined, gauge invariant, off-shell form factors, etc. In general, no, but at one loop, what we will study, it's perfectly well-defined. Now, normally when you do a one-loop calculation and you have a problem containing two scales which are very far apart, what you expect to find in a one-loop calculation is a logarithm of the ratio of those scales. Now, Sudakov form factors are the example where even at one loop, you find double logarithms in ratios of those scales. And that's the new phenomenon. And that's characteristic of processes wherever you have collinear particles in the game. This is generically what happens. So, we should do a one-loop calculation now of this form factor. And we will discuss this form factor at one loop without really doing explicit one-loop calculations, because I assume that you all know how to do one-loop calculations, but you also know that it typically takes a little bit of time to do it correctly. So, if you have questions about the technology, you can ask me and I will tell you what you would need to do. But I'll usually just give you the answer for the loop diagrams. So at one loop, what would we need to do? At tree level, of course, we have a single diagram here, where we have the virtual photon, the quark and the antiquark, and that would simply be a spinner. Let's say, let me give momenta to the particles p1, p2. That would simply be a spinner for particle 2. See, I have it differently. 2, 1, that would be a spinner for particle 1, gamma mu, and some spinner for particle 2. So totally trivial, of course, at tree level. If we go to one loop, we should multiply this by the wave function renormalization constant for the quarks, which itself is 1 plus order alpha s. Okay? And the renormalization constant you can just look up in textbooks, so I'm not going to bother you with that. But of course, at one loop, there's also a more interesting one loop diagram that we can draw. And this is really what we're going to study. It's this diagram where we exchange a gluon between the two quark lines. And let's assign a momentum to the gluon. Let's call this K. And then this is momentum K plus P2. and this is momentum K plus P1, and this was momentum Q, and Q is P1 minus P2. So you can work out what this diagram is. It just, unfortunately, it always takes so much time to do these things on the blackboard, but you get a color factor, which is CF, 4/3 in QCD. You get 2 powers of the strong coupling. We get in dimensional regularization a factor of mu to the 2 epsilon from the renormalization of the coupling, and then an integral d dk over 2 pi to the power d. The d is the dimension of space-time. Then u bar p1, gamma alpha, k slash plus p2 slash. You don't need to really work this out, but you should understand the structure in a second when I'm done writing. Gamma alpha u of p2. Yeah, somehow, I'm sorry, somehow I have my momenta in the notes opposite from my momenta on the blackboard. So let me turn this around. I have it like this. And downstairs we have k square plus I0. This is the Feynman I0. Then k plus p1 square plus I0, and then k plus p2 square plus I0. This is a calculation in Feynman gauge, C equal 1 gauge. And that's what you get. And of course, what you see here is we have a gluon propagator 1 over k square. And then for the quarks, the propagators are k slash plus p2 over k plus p2 squared, and k slash plus p1 over k plus p1 squared from these two Feynman propagators. The gluon vertex is here. The photon vertex is here. Okay, so I get an expression of that sort where d is 4 minus 2 epsilon. Yes, what? Yes, yes, yes. I treat this as a vector current, actually, not as a photon. If you want to treat it as a photon, you have to add an electric charge and a polarization vector. But to define the form factor, one usually leaves out these factors and just studies the matrix element of the vector current. Okay, so, this is an integral. You know how to do these integrals. I will simplify the integral. In particular, this integral, as you can see, is ultraviolet divergent because we have 2 factors of k upstairs, 6 factors of k downstairs. So this is ultraviolet divergent, but this divergence is not really interesting to my discussion here. So I will study a simpler integral. I will study instead a scalar integral. So it's a bit simpler, but it has all the interesting physics in it. And the integral I will study instead is the following. I add some prefactors here. I divided by pi to the power d over 2, mu to the 2 epsilon, and now integral d dk. Same denominators, so k square plus I epsilon, k plus p1 squared plus I0, k plus p2 squared. So the denominators are exactly the same as in the true integral, but instead of writing the complicated numerator, I will simply write something to make it dimensionless, 2p1, p2. and this is a dimensionless integral. This integral is not ultraviolet divergent. You can calculate it, and what you find in the limit where q square is much bigger than p square, what you find is that this is log of q square over p1 square log of q square over p2 square plus pi square third plus terms of order pi to the 4 over q square, where pi squared is minus little pi squared. And you just trust me that this is the correct value for this integral. You can do this integral, it involves some dilogarithms, and then you expand in the limit where q square is much bigger than p square, and that's what you get. And if I keep these external p squares of the quarks negative, it has the advantage that this big p square is positive, and then these logarithms are real. If you would take the little p squares to give positive values, you would pick up imaginary parts here. Usual thing. For which? Yes. I just said that. Then the result is still valid, but then you have a negative value argument under the logarithm, so you pick up imaginary parts. It's okay. I mean, you had a lecture on dispersion relations. Feynman loop diagrams can be imaginary, but if this is a massless quark and this is a positive p square, and basically these two lines, you can cut the integral here and get on-shell states, and then the integral picks up imaginary parts. I want to make your life as simple as possible, so I pick p square negative, no imaginary parts, and we get this simple answer. But if you want p square positive, then big p square is negative, and then you pick up I pi's from these logs. Still okay, the result is valid also in this case. This double logarithmic structure here is called the Sudakov double log. And this feature persists in higher orders of the loop expansion as well. So basically, for every loop order, you will pick up 2 powers of logs for this type of problem. So 2 loop, 4 powers of logs, 3 loop, 6 powers of logs, and so on. Good. Now, what we're going to do next, we have to speed up a bit. What we're going to do next is we're going to take this loop integral now, and we are going to compute it using the method of regions. The method of regions is a mathematical formalism developed by Smirnov in the 1990s to perform Taylor expansions of Feynman graphs. Basically, if you have a Feynman graph depending on more than one scale, such as this one, we have 2 scales, basically q square and p square. We could set the 2 p squares equal, then we have exactly 2 scales. If you want to evaluate this Feynman graph in a certain limit, q square much bigger than p square, you can do a Taylor expansion in powers of p square over q square, and that would be the first term in the Taylor expansion. And that's what the method of region allows you to do. Now, this method of region is a complicated mathematical theorem. It's not easy to prove it. Roughly speaking, what it does is that if you take a Feynman graph f, gamma, that's the original Feynman graph or Feynman integral, you can express this Feynman integral as a sum over So this is a graph. And you can perform it as a sum over subgraphs little gamma. And these subgraphs are obtained by applying an operation, which I call M gamma, on the original Feynman graph. And this operation says that you perform a Taylor expansion in the integrand of the integral in variables which are small in this subgraph gamma. So concretely, in this one loop diagram here, when we decompose this into region, we will, for instance, find a region where the loop momentum is hard, in the sense of hard particles. So the loop momentum has this scaling. If we want to see if this region is there, we take this Feynman diagram, as I wrote it down, we perform a Taylor expansion now, assuming the loop momentum is hard. So everything that's sub-leading, we throw away, and then we perform the integral. And then we get what's called the contribution from the hard region. And then we can ask, is this a leading contribution, or do we find something that's power suppressed? If it's power suppressed, we throw it away. So this symbol here means, you know, you can also write this out. This symbol here means that we only keep the leading, I mean, in the sense of a power expansion. We don't get the exact result, we're going to get the power series expansion of the graph. Next region we're going to explore, we say, well, what about if this gluon is collinear to particle P1 or P2? So here I changed the notation. I should also change it here. Again, we would say, well, what if the loop momentum is collinear? Then we know how it scales, then it has this scaling. Let's assume this scaling, let's perform a Taylor expansion of the integrand, then let's do the integral, see what we get from that region, and so on. And the statement is, if you do that with all possible subgraphs, you reproduce the original diagram as a series expansion. Never the exact result, but as a series expansion. But you must include all possible subgraphs. So that's the art, is to find what are the subgraphs that could contribute to this diagram. Well, this is a finite series. It's a finite set of regions, and then the sum of those regions will reproduce the correct result. Now, normally, to define these regions, we would, at least in our minds, we would introduce cutoffs again. We would say, you know, let's assume, for instance, if I say the loop momentum is of order Q, I somehow have to give it the scaling, but, you know, in my mind, I could imagine I draw a box in loop momentum space corresponding to the scaling, and I do the integral inside this box, introducing cutoffs, okay? But in reality, actually, we don't do that. In reality, we use dimensional regularization. And in fact, this theorem only works in dimensional regularization. And it works basically so this uses that in dimensional regularization. We have the following marvelous identity, that a dimensionally regularized integral of a scaleless integrand, something like 1 over k squared to some power a, is identically zero. You know, if you would look at this in your high school math courses, you would say, well, this integral is not zero. It's, first of all, it diverges at k equal to 0. It diverges as k go to infinity. It cannot be 0, it's infinity, okay? But the point is, these loop momenta have mass dimension 1. This is an integral with dimension d minus 2a. So this must be a mass scale raised to the power d minus 2a. The integral doesn't know any mass scale, so then its value has to be 0. It cannot be anything other than 0. So this is, in some sense, you may think this is completely dull, but this is a key identity in dimensional regularization. And because of this identity, this works. So for instance, I can take this integrand and I can say, well, what about a region where the value of k is much, much bigger than q? Infinitely much bigger than q. Well, take this integral, expand, assume that k is much, much bigger than q, and do a Taylor expansion. You would set everything to 0, p1 to 0, p2 to 0, okay, because it's all much less than the assumed k, and you would immediately get an integral of this type. So because of this identity, basically, scalings of k that have nothing to do with the scales of the problem, which in this case are q and p, will never give a contribution. If you're far away from q or p, you can always expand out all the variables in the integral. You will always get scaleless integrals. So that's, in a way, that's the key identity. In the notes, I have a few more comments on that, and there's also, I should say, there's also a very nice paper of Beneke and Smirnov, where this is explained in much more detail. Also for today, I uploaded a small exercise problem set for those of you who are still strong enough at the end of the day to do a little bit of exercises. And the first exercise is to take a loop integral, which is much simpler than this one, just a scalar integral with two masses, and perform the method of regions for this integral. And you should really do this exercise. The calculations are completely trivial, but you will see how piecing the different regions together, you reproduce the correct result. And I think you really need to see it in a simple example and to appreciate the method. But what I will do now, and I will do one more integral before the break, I will start now taking this integral and decomposing it into regions, and we'll do that until we reproduce the final result. Different regions in the loop momentum. Exactly. By the way, this is an approach irrespective of physics. The third problem on the homework is I just give you a difficult integral, not a loop integral. It's a one-dimensional integral over x of some function. And the function depends on the parameter, and I say evaluate this integral in the limit where the parameter is small. And you cannot do it analytically, but you can do it using the method of regions, and it gives you sort of the asymptotic expansion of this integral in the region where one of its parameters is small. So this is an incredibly powerful tool also outside of field theory, just if you want to do some hard integrals. So, okay, we're going to take this integral and we will decompose it into regions. Assuming that q square is much, much bigger than p square. And the first region, that is easy enough that we can do it before break, is the hard region. The hard region is the region where we assume that k has all components of order q. Okay? And all you need to do now, it's really not difficult, it's not magic. All we need to do now is we need to look at the three propagators and expand, if there is something to expand out components that are subleading under that scaling assumption. Now, if k is of order q, obviously k square is of order q square, so there's nothing to expand. But the first thing where we can expand something is k plus p1 squared. Because p1 is a collinear momentum, not all its components are big. Only one component is big. But all components of k are big. Okay? So it's simple basically. We write this down, k squared plus 2 k dot p1 plus p1 squared. Now k squared is of order q squared. Oh, well, anyway, let's first continue. This is a product of two momenta. I wrote you here how to write down the product of two momenta in light cone components. So we get k squared plus n dot k n bar dot p1 plus n bar dot k n dot p1 plus k perp p1 perp plus p1 squared. Okay? And here I forgot a factor 2. And now we count factors of lambda. So this is lambda to the 0 because it's hard. Nothing suppressed here. N dot k is lambda to the 0. And bar dot p1 for a collinear momentum is also lambda to the 0. Okay? And bar dot k is a hard momentum, lambda to the 0. N dot p1 is the small component. N dot p1 is order lambda squared. So this is order lambda squared. K perp is order unsuppressed lambda to the 0. P1 is order lambda, collinear momentum, and P1 squared is order lambda squared. So you see, I need to drop this, I need to drop this, I need to drop this. Simply throwing them away. You don't need to throw them away, but you need to expand them out here. You can tailor expand them out. If you want to work to higher order in the expansion, you keep the first order terms or the second order term. The key thing is you must expand them out from the denominators. You must really perform a Taylor expansion before doing the integral. For my purposes, I only want the leading order, so I'm simply throwing away these terms, and I keep only this guy. Okay? And the same for k plus p2 squared. Let me just write the answer. The answer is completely analogous. K squared plus n bar dot k n dot p2. And then everything else is power suppressed. And the reason is that in the case of an anticollinear momentum, it's n dot p, which is lambda to the 0, and all other components are suppressed. Okay? Now, here now I encounter in my loop integral light cone components of the loop momentum. In principle, there is no problem. But I'm going to use a trick now. I'm going to write this in the following form. I'm going to write this as k plus n bar over 2 times n dot p2. And this whole thing squared. You see the first term is k squared. The mixed term is n bar dot k, n dot p2. And the third term, which is the square of this, involves n bar squared, which is 0. So this is simply a trick to write this in something that resembles the original expression. And I will give a name to this vector here. I will call this p2 minus. This is sort of the minus component of this momentum p2. So I will call this k plus p2 minus squared. And likewise, I will call this k plus p1 plus squared. Okay, and now you do the integral. Oh, I also, sorry, there is one more thing I need to do. In the numerator, I have 2p1, p2. 2p1, p2. If we keep only the largest components, we get n dot p1 n bar dot p1, n dot p2. And this is the same, this is the two large components, and they're both equal to q. So this is q square plus higher order terms. So upstairs in the integral is just q square. And will be done in 1 minute. So now we have everything to compute the hard components of the integral. So the hard part of the loop integral is now I divided by pi over to the power d over 2, u to the 2 epsilon, integral d dk. Upstairs we get q square. Downstairs we get k square plus I epsilon, k plus p1 plus squared plus I0 and k plus p2 minus squared plus I0. It looks like the original integral. The only difference is the little plus and minus signs here. However, the key advantage is that there we had free momentum, q, p1 and p2, and we could form q square, p1 square, p2 square, and they were different scales. Here now, the scalar products are trivial. p1 plus square is 0, p2 minus square is 0, and p1 plus times p2 minus, p1 plus times p2 minus, you can easily check is equal to q square over 2. So basically the only scale in this integral is q square, and when you calculate it, you find the following result. And then we stop. This integral evaluates to gamma of 1 plus epsilon. And then now an expression. This integral is divergent. It will not, the original integral was finite, given here. This integral is not finite, it's divergent. That's not a problem. In effective theories, usually the integrals have different structures of divergences compared with the full theory. What is unusual is that you get 2 powers of the epsilon parameter, even though it's a one-loop integral. That's unusual. Also unusual, you get a 1 over epsilon pole, not just multiplied by a constant, but by a logarithm of mu square over q square. Then there is a double logarithmic term, 1/2 log square, mu square over q square, minus pi square over 6. Plus terms of order epsilon, which I'm not writing out. I was doing the expansion in epsilon. Okay, so basically, first of all, this proves that the original integral has a hard region, because this is not power suppressed, this is a leading order contribution. So we have found a contribution using the method of regions from the hard region. That contribution is divergent, badly divergent, double pole, single pole, plus a double log. The double log is not so bad, because at the end of the day, we get 2 powers of log q square. Here with the coefficient 1, there was a coefficient 1/2, not quite right. Okay, we'll see how this all works out later, the second lecture. But the key thing here is, this is the hard region, and the result can only depend on one scale, the hard scale. That's the idea in the method of region. You start from a 2-scale problem, and you write it using the method of regions as a sum of 1-scale integrals. In such a way that at the end of the day, when we sum up these contributions, we reproduce the Taylor expansion of the original expression. Okay, and at least that looks good for the hard region. It only depends on Q and the renormalization scale mu. No, it's not UV. This integral is UV divergent. You see it's 6 powers of k downstairs, 4 powers we integrate. It's all infrared divergence. No. At the end of the day, there are no infrared divergences. So we'll see that every region will be divergent, but the sum of the regions will be finite. I put an IR regulator there. I just, in the hard region, I need to expand it out. You see, the thing is, but we should really do a break. The thing is the following. If you give two-dimensional regularization, if you give such an integral, you all know how to evaluate this. You introduce Feynman parameters, you write it as a single loop integral with a more complicated denominator structure, right? But then at some point you do the Wick rotation and you use Cauchy's theorem, basically. You do the integral over the time component of the loop momentum, and there are poles along the contour. One pole is above the contour, one is below the contour. That's what we call a pinch singularity. And then, what is the loop integral? The loop integral is the residue around these poles, okay? So in a way, the magic of complex integration means that this loop integral, even though you integrate over the infinite momentum space, the loop integral at the end of the day is defined by the residue of the pole in the complex integration. Now, where are these poles? These poles are defined by the so-called Landau equations, okay? But these poles are, are determined by external variables, such as my q square, my p square, possible masses that could be in the integral. This is the variables that tell you where the poles are in the integral, okay? So in a way, in this way, the final result of the integral is a function of the external variables. If you don't give external variables, the integral is of this type and will be immediately zero. So that's the key thing here. So even though you may worry about, well, but I integrate out to infinity, isn't infinity important, you know, isn't that the region that gives the biggest contribution? No, at the end of the day, all that matters is where are the poles. And in a way, with this method of regions, we use that fact, right? So this integral, it turns out it has a pole that is determined by the hard region, and it has other poles determined by the soft region. So I split up the integral in a sequence of these poles. And by doing this Taylor expansion, you know, I'm expanding out small variables because in the hard region, they are irrelevant. They are not defining where the pole is in the hard region. Then I expand them out. Once I expand them out, the integral doesn't know the other region anymore because it doesn't produce poles. But I can look at the same integrand again and say, let me now look for a pole in the collinear region, okay? And then I do a Taylor expansion that expands away the poles in the hard region and only focuses on that pole. So in a way, I'm splitting up the integral as a sum over integrals that have poles in well-defined regions, depending on well-defined external variables. That's the principle behind it. Let's do a what? 20-minute break or?